Welcome. Now that we've understood how a MOSFET works, we looked at the MOSFET book qualitatively and quantitatively. Let's now focus on the MOSFET. So how does a MOSFET work? So a MOSFET, primarily as I told you, the MOSFET is the heart of the MOSFET. A MOSFET is used to induce charges in a piece of semiconductor, and then we apply a bias across these induced charges and create a conduction path that is able to conduct current. So let's look at a couple of ways to think about how a MOSFET works. Let's look at a piece of silicon which has a gate and an oxide on top of it. So at equilibrium, let's assume that the flat band voltage is set up in such a way that there exists a depletion region at equilibrium. Now, when I apply a positive voltage on the gate, the depletion region extends and eventually I create an inversion layer of, say, electrons in the semiconductor. So by applying a positive voltage on the gate, positive enough so that the depletion region eventually reaches its maximum width, and then the surface inverts to form an inversion layer. Now, I can use this inversion layer if I'm able to contact only the electrons in this inversion layer, and then if I can bias these two contacts, I can essentially get a current to flow. So how this would work is the voltage on the gate will ensure that an inversion layer is created at a certain voltage, and then if I'm able to bias this only the electrons, I'll be able to move the electrons from the negative to the positive terminal. So the key is to form a contact that talks only to electrons, because remember the rest of this here are holes. So you don't want to form a contact to the holes because then current is going to conduct in this fashion, right? So you want to create a contact which only contacts the electrons and does not allow holes to cross into it. So that can be easily achieved by using two N plus regions. So what is N plus? So we have a p-type semiconductor. We use the gate to create an inversion channel, and we contact the inversion channel only through the N plus regions of the device. So when the inversion layer is not formed, this structure looks like an N plus P N plus structure. These are two reverse bias diodes, and there's going to be no current flowing from source to drain. Current only flows from source to drain when I create this inversion channel, which is made up of electrons. And the N plus region ensures that this contact exists only for the inversion layer when it is formed, else it remains a rectifying contact for holes, not allowing any hole current to go through. So in this MOSFET, when I form the inversion channel, the current is purely driven only by electrons. Holes do not contribute to the current in this structure. Another way to think about the MOSFET, which sometimes helps students, is to look at the fluid dynamic model of the MOSFET. So let's assume that you have two tanks, a source tank and a drain tank that is filled with water, and you have a separator which is the gate. So right now there is no flow of water between the source and drain because the gate is preventing any water to flow from the source into the drain. Now let's apply a positive voltage on the gate or pull the gate down. When I pull this gate down, I create a path for the source and drain to talk to each other and the water equalizes. However, no current or no flow of water exists between the source and drain because both the source and drain are at the same potential. So water is stagnant. To get water to flow from source to drain, I need to also apply a positive voltage on the drain so as to get water to flow. So if I now apply a positive voltage on the drain, I now have created a level difference between the source and the drain, and hence water flows between the source and drain. I can treat that as the current. Now what happens if I increase the gate, or if I increase the gate voltage further? I essentially have a lot more water present here, so expect the current to increase. So expect the flow of water to increase when I increase the gate voltage, provided I have a level difference between the source and drain. Right? So to get current to flow, it's not only essential for the gate to be pulled down, but it is extremely essential that I need to have a potential difference between the source and the drain. Now at this gate potential, suppose I pull down the drain even further, then I've created a larger potential difference between the source and drain, and the current goes up. Right? So the current can go up, or the flow of water flow can go up if I pull the gate down, or I pull the drain down with respect to the source. Now what happens if I pull the drain beyond a certain point? Beyond a certain point, no matter how much I pull the drain beyond that point, the current is going to be limited, because the current is limited by this triangle of water. Right? So if I pull the drain further beyond this, the flow of water is not going to change, because it is now limited by this corner, which is the corner of the gate and drain. So pulling the drain further down from this point does not increase the water flow. So for every gate value, there exists a certain drain value over which the current does not increase. Or in other words, I can say that the water flow saturates at a given gate voltage for a given drain voltage. Beyond that, if I increase the drain voltage, I am not going to see an increase in the current flow. So what do we expect in the MOSFET? So let's recall and let's try and put the IV characteristics of this device together. So we know that a certain VGS is required so that I reduce the barrier for current to flow. And for current to flow, I need to have a certain drain to source voltage. So what we see is, if I plot IDS, the current between the drain and source, as a function of the gate to source voltage, I see that there exists a certain voltage which is known as the threshold voltage, below which no current flows in the device. Current begins to flow as long as I've applied a VDS and as long as VGS is greater than VT. And then I see that as I increase my VGS for that given VDS, I keep getting higher and higher current. Right? And that's because as I increase the VGS, I have a lot more volume of water that is flowing. So this increase in current is because of the fact that the volume of the water that is flowing is actually increasing. Now let's look at the other way to look at the transistor. Suppose I'm now going to plot IDS as a function of the drain to source voltage. Once I've created an inversion channel, what I see is that the current actually increases for small VDS and then it saturates. So beyond a certain voltage, a certain VDS voltage, the current does not change as a function of VDS. So this increase in current is happening because as I increase VDS, I'm increasing the slope of the water. So I'm increasing the speed at which the water flows. So this increase is different. This increase happens because as I increase VGS, I'm increasing the volume of the current, hence more current is flowing. In this region, my increased current happens because as I increase VDS, I'm increasing the velocity or the speed of the water. Beyond a certain point, I cannot increase the speed further, and so at that point the current saturates, leading to an ID-VD characteristic which looks something like this. So to recall, a MOSFET current is dictated by the minority carriers present in the semiconductor and which is modulated by the gate voltage. So always remember that the MOS cap, you need to first bias the MOS cap in inversion, create the inversion layer. Once that inversion layer is created, you can then use that layer to get a current to flow in the MOSFET. And finally, the MOSFET is a three-terminal device where the current is determined by the field between the source and gate and the source and drain. So current is going to be a function of not only the gate to source voltage, but it's also a function of the drain and source voltage. So this is the qualitative understanding of the MOSFET. In the next video, we'll develop a quantitative model for the MOSFET.